Hi everyone, this is Debasatam and you're watching the second lecture of EE635 Applied Linear Algebra. And this happens to be the third and final module of the second lecture. So what we were concerned with in this lecture is how to solve linear systems of equations Ax equal to B. What we have found out is that one very useful tool is this idea of equivalent systems. Equivalent systems are such that okay, system 1 and system 2 are said to be equivalent if every equation in system 2 is a linear combination of equations in system 1, and also every equation in system 1 is a linear combination of equations in system 2. Then they're equivalent, and we have found out that equivalent systems have exactly same set of solutions. The question is how to obtain these equivalent systems, and also how to obtain an equivalent system which is also easier to solve. Yeah, in this module, we'll define what we really mean by easy to solve, and we'll also see a method of how to a step-by-step method as to obtain um, such an easy to solve system of equations from a given system of equations. Yeah, by doing, as I said, a step-by-step method. Okay, so to proceed, let me share my screen. This should be visible. Yeah. So Ax equal to B is a given system of equations. I would like to solve Ax equal to B. To solve Ax equal to B by converting it into an equivalent system, which is also easy to solve. How do I do that? The first thing that I need to notice is the following. That, so you see, from the last module, we have seen that one way to do this is by multiplying A by M and also multiplying B by that same M. This is an equivalent system to the original one when M is invertible. If M is square and invertible, then this indeed is this new system is equivalent to the old one. But the question is, how do I get this M in such a way that this MA has some nice structure, easy to solve? That is why this idea of elementary row operation comes into the picture. What I mean by elementary row operation, let me define elementary row operations. Elementary row operations. Elementary row operations can be of three kinds. Yeah. Number one, so given a matrix, replace a row by multiplying every element in the row by a non-zero constant. This is one kind of row operation. The second kind is replace a row by that row plus a multiple of another row. You see, row operation one is actually replacing or substituting a row by a multiple of that, because when I'm multiplying every element in that row by the same constant, same non-zero constant, I'm actually looking at a non-zero multiple of that row. So replacing a row by a non-zero multiple of that is the first row operation. Second row operation is substituting a row by that row plus a multiple of another row. And the third row operation is permuting rows. Yeah. So this is, so each of these, remember, is actually like taking linear combinations, except for the third one, except the third one is not taking linear combinations as such, just writing the equations in a different order. That's what permuting the rows really mean. Now, so how do we actually codify? So how do we know that these are indeed, these are going to give us equivalent systems? So let us notice each of these row operations. Let us try and dissect, try and work on these, each of these three row operations, one after the other, one by one. Okay, so let us first look at row operation number one. What are we doing? We're replacing every row by a multiple of, replacing a row by a multiple of that. Okay, so think of the matrix A, which is nothing but A11, A12. I'm writing this matrix again and again, and I would keep doing that throughout the course. So you should not get tired of it, in fact. This was my matrix. And suppose there is an ith row somewhere here. Row operation 1 would replace the ith row by, say, alpha times ith row. What we are going to write for this is row 1, replace row 1 by c times, replace row I by c, replace ri by alpha times ri. What is that? What should that result in? That should result in, so this is some a hat generated by, so hang on, I'm going to write this again. 1 2 a1n, a21, a22, a2n, dot dot dot. There is an ai1, ai2, dot dot dot, ain, and of course there is finally am1, am2, amn. But the ith row has been replaced by alpha times that, so alpha, alpha, alpha will appear here. Okay. How do I know that this a hat, and correspondingly when I do this to b hat, so b hat will change to b1, b2, dot, 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 up to alpha times bi, and then dot, 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 bm. This is going to be b hat. How do I know that this a hat, b hat is equivalent to my old original system? Notice that the corresponding M matrix, the matrix M, is going to be the following. Matrix M, let us notice. Suppose I have 1, 0, 0. Okay, before I show what this M is going to be, I need you to observe the following. Suppose I have 1, 0, 0, dot, 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 0. This multiplies to A. What would be the result? This is 1, 0, 0. So go back to our observation 2 in the last module. This is row operation. Sorry, this is linear combination of the rows of A. Yeah. What linear combination? What linear combination? 1 times the first row plus 0 times the second row plus 0 times the third row and so on. Yeah. This is nothing but A11, A12, dot, 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 up to A1n. That's what. Similarly, so this vector, by the way, will be called E1. right? So similarly, E1 transpose, in fact, E1 transpose. Similarly, if I have 0, 0, dot, 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 1 at the ith position, and then 0, all zeros, just 1 at the ith position, that multiplies A, what would be the result? This will be AI1, AI2, dot, 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 up to AIN. It picks up the ith row of the A matrix. So this is coded as EI transpose A is nothing but the ith row of the matrix A. Okay. So now, now when I have M multiplying A, and I want the effect of M multiplying A to be the ith row being changed by, being substituted by alpha times the ith row, what should I do? First row should remain unchanged. So then that means the first row of M should be 1, 0, 0, all zeros. Second row should remain unchanged. So 0, 1, 0, 0, 0. This should continue till I have 0, 0, 0. At the ith position, if I put an alpha and 0, then see what happens. 0, 0, 0, 0, 1. So this is almost like an identity matrix, but at the ith position, I have, instead of 1, I have an alpha. And this one multiplies A, the result of the product will be first row of alpha, first row of A. The first row of this product will be first row of A, then second row of A, and so on. Only at the ith row level, it will get, ith row will get multiplied by alpha. Yeah. So this M in fact encodes row operation number 1. Row operation R1 being substituted by alpha times substituted by R, alpha times R. Yeah, you can quickly check R1 alpha times R1. What would this matrix be? The corresponding matrix M is alpha 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0. Yeah, like this. Now, coming on to the second row operation. Second row operation says what? Second row operation says that, okay, replace a row by that row plus a multiple of another row. Let us try and do this for row number 1 and 2. You'll do it in general as your immediate attention problem. I will show it to you very soon. So, row operation number 1. So, suppose I want to change row number R. Say I want to substitute R2 by R2 plus alpha times R1. Okay, what should I do? What should this M be? So M times A I have to do, right? So only R2 is going to be changed. So R1 remains unchanged. R1, so therefore the first row of M will remain the same. Second row of M will be, let me write this down and then you check this. And the rest of them are going to be just as they would be for an identity matrix. This is M, this multiplies A, that produces the desired result. Now the question is why. So when I do this one, this row, notice this row. So this row once again has every entry 0, only there is a 1 at the second position. Oh, sorry, I made a mistake. I made a big mistake. This is unforgivable. 0. This ought to be 1. So this ought to be alpha. This is alpha. Now here, when I do this, what happens? See, everything else is 0, only alpha is here and 1 is here. So the linear combination will be, so the second row of this product, so the first row will be just A11, A12, dot up to A1n. The second row will be alpha times the first row of A plus 1 times the second row of A, which means this is going to be alpha A11 plus A21, alpha 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 A12 plus A22 dot 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 alpha A1n plus A2n, and then again it will be A31 A32 dot 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 A3n AM1 AM2 dot dot. See, everything else remains exactly the same. Only the second row gets changed by second row plus alpha times the first row. So that is how it's going to look like. Your immediate attention problem will be to describe what will happen to this in general. Say Ri is substituted by Ri plus alpha times Rj. How do you encode that as a matrix? That also you can do. Row operation number 3 is in fact even simpler, right? So once again, I'm going to do it for 1 and 2. So suppose I am saying that, okay, A hat is as follows: A21, A22, dot, 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 up to A2n, and this is A11, A12, dot, 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 up to A1n. Everything else remains the same: A31, A32, dot, 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 up to A3n, dot, 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 AM1, AM2, and everything else remains the same. Only these two have been interchanged. These two have been permuted. How do I get this from? How do I get this from A? What should M be in that case? Well, in fact, you see, the first row of this product should be such that it picks out the second row of A. Then this should be 0, 1, 0, of course. And the second row should be such that it picks out the first row. So it should be like this. And the rest will just be as they would be for an identity. This is the M matrix. This multiplies A and it produces the desired A hat. That's it. That's the permutation. Your immediate attention problem is, of course, do it for ij. So that means row I gets substituted by row j, and row j gets substituted by row I. How do you do this? Yeah, this is all okay. What is even more important is the fact that all of them are invertible. All of these m's are invertible. Indeed, for the first case, this one, let me show you. M being equal to 1, 0, 1, 0, 1. Let me do it properly. Zero, 0, alpha, 0, 0, 0, 0, 1. This was M, right? What is M inverse? M inverse going to be M inverse is going to be just alpha inverse here. That's it. For the second case, when m is, so I did this particular one, right? Let's do for this one only. The general one you will do as an immediate attention problem. For this guy, m inverse would be, just go and check, m inverse is going to be minus alpha. Yes, that's it. And for the permutation case, where m is equal to 0, 1, 0, 1, 0, 0, then just like what they would be for an identity, for this, m inverse is nothing but itself. Yeah. So all of them are invertible, which means when I do these operations, they indeed are, they give me equivalent systems. Not just that, when I do, so suppose M1 is such a row operation matrix. So by the way, these matrices will be called elementary row operation matrices. So when I have an elementary row operation matrix like this, so suppose I have an elementary row operation matrix M1, elementary row operation matrix M2. So first I do M1A, this row operation, and then on that I do M2. Together, suppose they obtain A hat. Is this also equivalent? Well, of course. Why? Because I could just do M2 inverse M2 M1A. That would give me M2 inverse A hat. But then this is nothing but M2 M2 will cancel out. This will be M1A. M1A is just M2 inverse A hat. Now if I do M1 inverse, I will have M1 inverse M2 inverse A hat, which will be A is equal to M1 inverse M2 inverse A hat, which means nothing but that from A hat also you can obtain A. So equivalent, right? It's invertible. So in fact, what it shows is that we already know that product of invertible matrices is also invertible. And that is what we are using here. In fact, this M1, M2, all of these elementary row operations, they are all of them invertible. So any finite product of that is also invertible. So therefore, it makes sense to define this particular thing, row equivalence. Two matrices, A, B, both of them of the same size, are said to be row equivalent if there exists a finite set of elementary row operation matrices M1, M2, up to MR, such that B is equal to MR, MR minus 1, M2, M1, A. That is, I start with A, I do elementary row operation M1, I go to A1, I do elementary row operation M2, I go to A2, and so on till I have M till I multiply by MR and I get AR, which happens to be B. Then A and B are said to be row equivalent. Of course, obviously, because these are elementary row operation matrices, there will be these inverse matrices also. M1 inverse, M2 inverse, M3 inverse, and so on, MR inverse, which takes B to A. Earlier we had A to B because they are in elementary row operation matrices, so invertible. So this inverse operations will take us from B to A. So such things will be called row equivalent. Okay. Now, what do we do once we have row equivalence? What do we do when we have row equivalence? This is where the question of this is where, not question, the definition of easy to solve comes into the picture, right? We will see it in more detail in the next lecture, but let me just introduce the topic. What is easy to solve? How do we define it? Yeah, that easy to solve definition comes via the definition of row reduced. A matrix A is said to be row reduced if, number one, all these properties have to be satisfied. Number one property, A has the first non-zero entry in every non-zero row to be equal to 1. Such an entry would be called, okay, let me just pause this for a bit. Yeah, and we are back. I was saying that these entries, these ones, will be called leading ones. Okay. Number two property that has to be satisfied is that every column containing a leading one must have every other entry equal to 0, right? So a matrix A of size m cross n is said to be row reduced if A has the first non-zero entry in every non-zero row to be equal to 1. Yeah, these will be called leading ones. And every column that contains a leading one must have every other entry to be equal to 0. Right? Yeah. If these two properties are satisfied by a matrix, then the matrix is said to be a row reduced matrix. We can see an example of a row reduced matrix. Say we have a matrix that looks like 1 0 0 0 0 1 0 0 0 1 0 0 0 0 1. It's an identity matrix. This is row reduced. See, these are the leading ones. This is the one, this is the one, this is the one, and everything in their columns appear to be like that. Okay. I said first non-zero entry. So first non-zero entry from the left. It's understood that from the left. Similarly, I can also have something like say 0 0 1, and then say 2 and 3. Then have 0 0 0 0 1 5 4 0 0 0 0 0 1. Is this row reduced? Well, no, because you see for row 1, there is a leading 1 here, true, but that leading 1 has this 3 appearing here, then that makes this not row reduced. So what I can do is, this however will still doesn't have that problem, but still there are problems like this is also a leading 1, but this also has this column which are non-zeros. So I just have to make them zeros. Yeah, this is a row reduced matrix. Similarly, I may also have something like 1, 0, 0, 1, and then 2, 5, 0, 0, and then suppose I have 0, 0, 0, 2. Let me make this guy 0. This almost is row reduced, but there is one issue here, namely this is not a leading 1, it's a leading 2. So this is not row reduced. I have to make this guy 1 in order to have row reduced form. So this is a row reduced matrix. So I hope you understand what row reduced matrices are. Okay. Yeah, is that all right? Now, once we have row reduced, what we need to notice is the following. Of theorem, every matrix A is row equivalent to a row reduced matrix. Proof, once again, very simple. I'm not going to do a complete proof of this. This is kind of tedious. I'm just going to give you a sketch of the proof. Okay. So suppose I have this matrix. What I'm going to do is I'm going to scan through these rows from the left. So first I start with row number 1. I scan from the left. Suppose I get a 0, I get a 0, I get a 0. Yeah, I get a 0. Possibility is that I'll get all the zeros. Then I don't do anything. I just go to the next row and do 0. And once again do the scanning. Suppose I get a 0, 0. But now suppose I get a I get something non-zero. You know? Suppose I get something non-zero. And then I don't worry about the other entries. What I do is I do an elementary row operation and make this guy 1 by doing a elementary row operation. That is allowed, right? I can just multiply by the inverse of that number to that entire row, and that multiple of the row will have this guy to be 1. This is how I get a leading 1. And then with this leading 1, I just run through every entry in the column by doing row operation, making them zeros. How? So suppose this entry is non-zero. Suppose this entry is some A or something. Let's say some A. I just do the row operation that replace this row by minus A times the second row. Make zero here. Similarly, I scan through every element in that column and I keep on making them zero. If it is already zero, I don't do anything. But if it is not zero, then I make it zero. So that way I produce zero in every entry in that particular column that contains the leading one of row number 2. Okay. Now I move to row number 3 now. In the row number 3, once again I start scanning. If I get a zero, if I get all zeros, then I move to row number 4. But suppose I encounter a non-zero entry here. If there is a non-zero entry here, once again I can make it 1 by doing an elementary row operation. I make it 1, and then once again I decimate through all these entries in the column and make them 0. I don't have to do anything above because they are already zeros. But suppose suppose the situation is not like this, but instead suppose I already have zeros here, but the first non-zero appears here, which I make 1. Then I have to decimate, I have to create zeros even on top, not just below, but on top also. But that also I can do. And remember that because this, this leading one has created all the zeros below here, like this. Yeah. When I do this back substitution of changing the rows above, this one remains unchanged because it has already created zeros in its column. So they don't change by these row operations. So the leading ones don't change. So that is how I create these leading ones and make sure that the columns containing leading ones have only the leading ones and everything is 0. So that is how I convert a matrix to a row reduced matrix. Second form would be what is known as row reduced echelon or row reduced echelon. Echelon means hierarchy, right? Like highest echelon or something. Like, for example, you can use the word echelon in a sentence like Rabindranath Tagore was in the highest echelon of intellectual thinking, right? Something like that. So row reduced echelon form. So what is row reduced echelon form? So a matrix, once again, A is said to be, we'll use this abbreviation, said to be in RRE form, row reduced echelon form, if it satisfies the two properties. Number one, all rows, three properties. First thing is A is firstly, of course, row reduced. Secondly, all the 0 rows, that is rows containing only zeros, appear below the non-zero rows. That means a row that has every entry 0 must appear at least below the rows that have at least one non-zero entry. Okay. Then number 3 is, okay, K1, K2, K3, up to KR be the positions of the leading ones of rows 1, 2, 3, R respectively. Suppose there are R non-zero rows, then there are each non-zero row must have a non-zero must have a leading one, right? And those positions suppose are K1, K2, K3 up to KR. Then they must satisfy K1 less than K2 less than K3, dot, 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 this one, okay. Right, the leading ones must satisfy something like this. So what would be an example of a row reduced echelon form? So of course an identity matrix is a row reduced echelon form. It's in row reduced echelon form. Take K1 here is K1 is 1, K2 is 2, K3 is 3, K4 is indeed 4. Something that is not row reduced echelon but row reduced is a permutation matrix. Yeah, 4 by 4 permutation matrix. This is row reduced, but this is not row reduced echelon. I hope you understand. Now, just a corollary of the earlier result. Every A is row equivalent to a matrix in RRT form. Of course, yeah, just do row reduction, make it row reduced, and then just change the rows, permute the rows in such a way that the result becomes a row reduced echelon form. Yeah, before we finish, so this is where we are going to end today's lecture. Before we finish, once again, I have these companion problems for you. IA3, and for m equal to 3, write down all the matrices for the elementary row operations and the inverses. Repeat IA3 with n equal to 4. IA5 says write a 3 by 5, 4 by 5, 5 by 4, 4 by 4 matrix in RRE form. And give an example of a 4 by 4 matrix that is row reduced but not RRE. Right? Do these exercises. Yeah, till we meet for the live interactive session. Let me stop sharing my screen. Oh, sorry. Okay. So I hope you enjoyed this lecture. In the next lecture, we'll see how this RRE form, which is actually any matrix can be converted to RRE, how this actually becomes a simpler system of equations. It means simpler to solve, easy to solve. That will be the part of the next lecture and the corresponding things that come out of it. Okay. I hope you enjoyed today's session. Please give your comments, your feedbacks in the comment section below or in the Google Classroom also. All these things will be counted. Uh, your your uh, involvement in participation, in these discussions will be very much encouraged. Okay, so I guess that's it. I don't think I have anything more to say now. Uh, right, all the best. Take care of yourselves and stay safe, stay home, stay healthy. All right, bye bye then.